Hello, my name is Stephen Earls and I work as an area coordinator with the Further Maths Support Programme in Wales. If there is anything in the following slides that you would like clarification on, or anything that you would like to ask a further question, then you can contact me at either of the two email addresses that are on screen at the moment. And that will also apply with regards to any questions that you have with regard to the worksheet that supplements this presentation. This presentation is going to look at proof and its importance within the area of mathematics. Now, proof itself can take a variety of forms, but it is, as it says on the screen, a fundamental aspect of mathematics. You need to be able to prove things for the whole number system, not just the first million, 2 million, 20 million. You need to prove it for every single number. Now, some of the forms of proof are by deduction, by exhaustion, by contradiction, or by induction. The first three you could possibly have met up to GCSE, but certainly at A-level mathematics you will meet deduction, exhaustion, and contradiction. The proof by induction is specific to the Further Maths Unit 1 course. Quite often, the proof by induction is also called the domino effect. If you can prove that the first domino will fall over and hit the second domino, then the second domino will fall over and hit the third domino, and so on. Now, as I say, proof is a fundamental basic of mathematics. If you take, for example, Pythagoras' theorem, that was proved for a squared plus b squared equals c squared. And it finally came to a proof back in the late 20th century, where it was proved that if you went above the power of 2, so you went to a cubic or power 4, power 5 or larger, then it didn't work. Now, there is one mathematician called Goldbach who has a conjecture, and the conjecture is that any even number after the number 2 can be written as the sum of two prime numbers. Now, in quite a few cases, it can be in more than one way. Now, Goldbach only has a conjecture. It is not Goldbach's theorem. It has never been proved for every single number. And the problem with Goldbach's conjecture is that he states it can be written as the sum of two prime numbers. And that's where it falls down, because we cannot find every single prime number. So every time somebody says this is a new prime number, they've got to go through a rigorous proof to see whether or not that one is a prime. And obviously we're only up to a certain number of digits and we don't know anything beyond that. So that's why it's still a conjecture. Now, these two questions here, they are both examples of a proof by deduction. Now it says, question 1, prove that the sum of three consecutive numbers is divisible by 3, and the second one, prove that the sum of two odd numbers is always even. Now the second one, really and truly, we should as teachers be getting you as students to prove odd and even numbers back in about year 8, year 9. And if we do that, then these become much, much easier. Now, in terms of the solutions of these, what we have is as follows. So for question 1, we'll say that the first number and number I abbreviate to NO full stop, we'll call N. So the second number we'll call n plus 1 because it's 1 bigger. And then obviously the third number, we'll stretch our imaginations, is n plus 2. So the sum, if I put these in brackets, it's easier to see. Is literally n plus n plus 1 plus n plus 2. And that will give me 3n plus 3, which is 3 brackets n plus 1. Now, as you can see, I have a common factor of 3, which I've taken it outside the brackets, which means that we've got 3 times a number. Now that number is worth n plus 1. And if you notice, if you look at the 3 numbers that we started with, it's 3 times the middle number. But because we've got 3 as a common factor outside, the total will always be divisible by 3. So we can say here, therefore, divisible by 3. Divisible by 3. There we are. So that's where that one comes in. But it's about that first choice. The first number is n. Now normally when we're looking at proof, we will look at n, m sometimes. We tend not to use x very often in proof. Generally in the rest of mathematics we tend to use x, but in terms of proof we start looking at n for number. Now the second one said show that the sum of 2 odd numbers is always even. So again we'll look at this. Now what we should have is that the first odd number, and I'm just going to write first odd and then n for number. Now if you think back to when you were in primary school, you very quickly realized that if you had a number n and you said, right, I want 2 of those, so you went through the 2 times table, you very quickly realized that if you double a number, you always had an even answer. So then I'm going to say plus 1. Now, I can hear some of you say, but hold on, couldn't an odd number be 2n minus 1? And the answer to that is yes, it could. I tend to go with plus 1 because I tend to prefer working with plus symbols. I can work quite easily with negative symbols, but the plus symbol at the introduction just does tend to make it a little bit easier in the workings out. So that's my first odd number. So if you say to a class full of students, think of a number, double it and add 1, and then say, right, hands up those who have got an odd number. Every single hand in the class goes up. So that's a guaranteed odd number. So we do a similar thing for the second odd number. Now, with this one, we can't use n again. So we move on 1 letter in the alphabet. We pick a different letter, m, which means we've got a different number to n. We double it and we add 1. So those are my 2 odd numbers. Again, if I put them in brackets, the sum is equal to 2n plus 1 in the first bracket plus in the second bracket 2m plus 1. Now, remove the brackets and add will give me 2n plus 2m plus 2. Take out a common factor of 2, twice brackets n plus m plus 1, and what we'll have there is we have this common factor of 2 outside. Now, irrespective of the values of n and m that any particular student chooses, we add those two numbers, n plus m plus 1. That doesn't matter if that is odd or even. As soon as I double it, I will end up with an even number. So that because of that common factor of 2 outside the bracket, the sum of any two odd numbers will be even. So therefore, sum of any, and I'm putting that in capitals because I've proved it there beyond a shadow of a doubt for every single odd number in existence. So irrespective of what you choose for n, irrespective of what you choose for m, you will always have two odd numbers added together giving an even total. So the sum of any two odd numbers and numbers is abbreviated to NOS, full stop. The sum of any two odd numbers is even. And there's my proof. Nice, elegant, and it works for every single particular value. So as you can see, this whole concept of proof need not necessarily be scary or frightening. We can take it back to basics. Now, with the next question, it's split into two sections. Prove that the square of a single digit number cannot end in 8, and what happens if you consider double digits. So if we take the first part, prove that the square of a single digit cannot end in 8. This is an example of proof by exhaustion, which means you do every single digit number, you square it, and you see what the answer is. So that's what they mean by proof by exhaustion. They'll give you, say, 4 numbers, you work through all those 4 numbers and see if the answers agree to the statement given. So that is proof by exhaustion. So as far as this one is concerned, we would literally do 1 squared equals 1, 2 squared equals 2, lots of 2, which is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. So as you can see, you're working through each and every single one of these. 7 squared is 49, 8 squared is 64, and 9 squared is 81, and for the purists amongst you, 0 squared equals 0. So as you can see, by proof by exhaustion, the question was, do any of these, when I square them, the single digits end in an 8? I look at it and the answer is no, right? So that is a proof by exhaustion. Now that's quite a long proof by exhaustion because technically we've worked through 10 digits there. They don't like to do that if they give you a proof by exhaustion, they limit how many numbers you can actually physically work with. Now, for the second part, it said, what about double-digit numbers? So, as far as that one is concerned, what we need to do is we need to say, let the number equal AB. Now, that number AB means A in the tens column and B in the units column. So technically what we have is, if A and B are single digit numbers, we actually have 10A plus B. So that's what AB actually means. 10 lots of A plus B. So if you think of, I don't know, 74, that's 7 lots of 10 plus 4. So if we square that number, so AB squared actually means 10A plus B all squared. So from the work you've done at GCSE, you square the first, 100A, you multiply the two things together, 10AB, and double it. So that will give you plus 20AB. And then finally, plus B squared. Put the squared in. Now, if we think about the work that we've done starting back at primary school, a single digit multiplied by 100 gives me a 0 in the units column. So that has no implication to what's happening in the units column. A times B multiplied by 20 again puts a 0 in the units column. So again, that does not contribute anything to the units column. The only item that contributes to the units column is B. And when we square B, from the work we've done on the previous slide, none of those numbers end in 8. So a two-digit number cannot end in 8. All right? So therefore, a two-digit number, when squared, cannot end in 8. So that's taking your knowledge of what happens when you multiply by 100, what happens when you multiply by 10. So we need to be thinking very, very carefully about the work that we've done lower down our academic careers. So it's not just all about this is the new stuff, this is all important. We can never ever forget the work that we've done previously. Now the next question, this one, as you can see, was taken from the University of Aberystwyth Scholarship Entrance Exam. And this question was a good few years old. But I love this question. It's a really, really good question. Because if you go through the question and pull apart each of the concepts, then this question is, the whole knowledge base of this is complete by the time you get to year 8. You know, just prove that the square, well, even if you don't square numbers in primary school, by the time you get to year 8, you know what a square number is. By the time you leave primary school, you know what an odd number is. When you divide it by 2, there's always a remainder of 1. What happens when you divide by 4? Again, that's a concept you first met back in primary school. And the concept then of leaving a remainder of 1, that is also primary school. 5 divided by 4 is 1 remainder 1. 7 divided by 4 is 1 remainder 3. So we're used to doing that in primary school, and it just builds up from there. Now, what makes this a scholarship question is that because it's a proof, we need to use algebra. And once that algebra kicks in, that's where the proof comes in. So that's what we need to do. Now, as far as this question is concerned, again, we go back to the work we did on adding odd numbers. So we say, let odd number equal 2n plus 1. And again, for the purists amongst you, I could just as easily have written 2n minus 1. If I double a number, it's even, and then I either add 1 to make it odd, or I take 1 to make it odd. Personally, as I said before, I prefer to add 1. Now we're asked to square this number. So we want 2n plus 1 all squared, which is 2n plus 1 times 2n plus 1. And that will give me 4n squared plus 2n plus 2n plus 1. Add together common terms, 4n squared plus 4n plus 1. From the first two terms, I'm going to take out a common factor of 4. I am not taking out a common factor of n as well. And then plus 1. Now, the question said, show that the square of any odd number when divided by 4 has a remainder of 1, or always leaves a remainder of 1. Well, if we look at this, if we take the bracket term, I don't care what number you choose for n, because n squared plus n gives a value, but then I'm multiplying it by 4. So the first two terms have a common factor of 4, irrespective of the choice of n. Now, I can divide that bit by 4 and it gives me an exact value. But then we've got the plus 1 left on the end. So the first part is divisible by 4. So first part, this is where the writing doesn't quite keep up with the speech. First part is divisible by 4. With a remainder of 1. So that's why the square of any odd number, when divided by 4, always leaves a remainder of 1. And that's exactly the way it works. So again, we've proved it there for every single odd number that exists. And that's exactly what we want for proof. We want to prove it for every single value. Not just, oh, these 4, these 5, these couple of million. Every single question going. Now, this next one, a prime number followed by a square number. So as the example is there, you've got 1, 2, 3 is prime, 4 is square, 5, 6, 7, 8, 9. Is this 3 followed by 4? Is that the only case for the whole of the positive number line? And the answer is either yes or no. But we can't just say yes or no. I need to show you that it's yes it is or no it isn't. So it's that concept of proof. Now, I mentioned earlier about goal-back and the problem of selecting a prime number and coming up with a rule for a prime number. So in this case, we might be better looking in this case at the square number and then taking away 1 because that's what it says. A prime number is followed by a square. So a square number is preceded by a prime number. Now, in terms of the solution of this one, if we say let the square, and so we've got let the square number equals, let's call it n squared. And again, if you notice, we're using n for number, and it's a square number. So say, call it n squared. Don't call it n, because then you start to introduce square roots, and I don't like working with them. I can, but given a choice, I'd rather not. So I work out strategies on how not to do it. So the prime number is 1 before that. So therefore, prime number equals n squared minus 1. Now, those of you that can remember from your GCSE course, I think a lot of staff introduce it or call it by the time you get used to it, dots. Difference of 2 squares. And that's exactly what that prime number is. We've got n squared minus 1. So technically we've got n squared minus 1 squared. So we can write this, but n squared minus 1 is equal to n minus 1 as 1 factor multiplied by n plus 1. Now, those of you that move on to look at A-level maths, both the ordinary mathematics A-level and the further maths A-level, the difference of 2 squares becomes far more important, and it becomes a very valuable working tool that you need to be able to recall at an instant's notice. So you need to get used to using that. Now, I've said there that n squared minus 1 is a prime number. Now, again, if you think back to primary school, bottom end of secondary school, a prime number, what you were told, so as n squared minus 1 is prime, this implies 1 factor is equal to 1. So either what we have then is, so therefore, either n minus 1 equals 1. So this implies n equals 2, or n plus 1 equals 1. So this implies that n equals 0. So if we take those two values for n, what we can then say is that if n equals 2, the square number equals 4 and the prime number equals 3. And if n equals 0, then the square number equals 0 and the prime number equals -1. Now, technically, the question said on the positive number line. So that means that this bit here can be ignored. I don't need that bit because that's not on the positive number line. So this is the only case. Now, the whole thing about this one required you to use the difference of two squares to factorize and then say, right, I've got two factors. When multiplied together, give me a prime number. I know that the definition of a prime number of those two factors, one of them has a value of 1 and the other one has a value of the number itself. So that is why it is so important to keep going back and checking to make sure that you've got all the work from year 11 and below at your fingertips, that you haven't forgotten them and that you will keep using them. Now, the next question, as you can see, and I've done it in both English and Welsh, it says prove that the left-hand side, 3x over 2 minus x minus 6 over 5 plus 2x plus 3 over 7 equals 111x plus 114 over 70. There is a clue there as to how to answer this question. If I look at the denominators on the three fractions on the left-hand side of the equivalent sign, that's not an equal sign because it's got three lines, it's an equivalent sign. I've got a 2, a 5 and a 7. If I look at the denominator of the fraction on the right-hand side, I've got 70. And strangely enough, 2 times 5 times 7 gives 70. So that's how I find my common denominator. So always use the question. Go back, look at the question and say, yeah, I know how this works. I can put it together from the information that you've given me within the question. Now, in terms of that, the solution to this one is that you will split it up into two sections. But prior to doing that, when you see the question and it's written, you will write it as 3x over 2 minus, and I'm going to put a bracket around here, x minus 6 all over 5, and then plus 2x plus 3 all over 7. And the 2x plus 3 is also in a bracket. And that is equivalent to 111x plus 114 all over 70. Now the reason I've put it in brackets is that if you don't put it in brackets, you will make a mistake with the symbols. Because what a lot of people forget on that second one is it's minus times x and minus times minus 6. And if you don't put the brackets in, then you will forget to do it. Now, with this type of question, it is perfectly valid for you to say, right, the left-hand side, I'm going to take each fraction and put it all over 70. So it's all going to be over 70. So 2 goes into 70 35 times. So we're going to do 35 lots of 3x. Then we're going to do minus 5 goes into 70 14 times. So it's 14 lots of x minus 6. And then plus 7 goes into 70 10 times. So it's 10 lots of 2x plus 3. So now remove the brackets and we get 105x minus 14x plus 84. And if you don't put the brackets in, somebody somewhere will write that as minus 84. So that's why it's important you put brackets in. It's like when you're solving questions on quadratic equations and you're substituting in the negative number into the formula, or into any formula, come to that. When you substitute the negative number into a formula, put it in a bracket, because you're immediately saying to yourself, you've got to be careful here. I've got to think before I do. Engage brain before doing work. And that's what the bracket does, is it makes you think carefully. So removing the final bracket gives me 20x plus 30. And that's all over 70. And collecting together like terms. And that will give me 20 take away 14 is 6, plus the 105 gives me 111x. 84 plus 30 gives me 114 plus, and that's all over 70. And if you go back to the start of the question, you'll say, oh, hold on, that is equivalent to the right hand side. And that is a very valid proof, proving that the left hand side can be written as the right hand side. So again, look at what they give you in the question. Don't just think, oh, where do I start? There are clues and subtle hints within the question. Go back, look at them. Why are they picking 2, 5 and 7 and 70? They could have chosen really awkward numbers. They didn't. What they chose to do was to give you numbers that were there and you could read them and pick them out. Now, as far as the next question is concerned, as you can see, it's in English and Welsh again. It's from the AS Mathematics Unit 1. It says, given that n is an integer such that 1 is less than or equal to n is less than or equal to 4, prove that this is a prime number. This is a method of proof by exhaustion. If you notice, they have limited. N can only be 1 or 2 or 3 or 4. There's only 4 options. They're expecting you to work them all out. So that's why they do a proof by exhaustion. They limit what you're actually working with. So for this particular question, you would have that obviously you've got 1 is less than or equal to n is less than or equal to 4. And we've got 2 n squared plus 5. So you literally go n equals 1. So we've got 2 lots of 1 squared plus 5. And that comes to a grand total of 7. And that is a prime number. So far so good. We then move on to n equals 2. So we've got 2 lots of 2 squared plus the 5. And that equals 13. And again, that's a prime number. Then we try n equals 3. So we've got 2 lots of 3 squared plus 5. And that comes to 23. Strangely enough, 23 is also prime. Then we try n equals 4. So we've got 2 lots of 4 squared plus 5. That's 37. And that's also prime. So 2n squared plus 5, where n is any number between or including 1 and 4, it's prime. If you notice, they've limited it. I would imagine the reason for that is, one, it's time consuming to work through anymore, and secondly, you're going to come to a stage where, strangely enough, it doesn't work. So we just need to be careful. I think if n is 9, it doesn't work. It comes out as 9 9's 81, 162, 165, which isn't prime because it ends in a 5. So as soon as you get to 9, this formula doesn't work anymore. And again, sometimes it's the little simple things. They want proof by counterexample. The best question I can think of for that one is every prime number is odd. Nice easy statement. Every prime number is odd. And then every student puts their hand up and goes, excuse me, 2 is a prime number, but it's not odd. Therefore, my statement is wrong. Not every prime number. So far, we've proved all bar 1. And that's the way it is. 2 is a prime number, it's even, so we cannot say all prime numbers are odd. Nearly all, most, all bar 1, we can say all those, but we can't say all prime numbers. Now, the next bit, again, is an AS one. And again, I've chosen this one because of the fact that you learn two new bits of information for the AS mathematics, and this becomes an easy 3-mark question. Now, as you can see there, prove that sine cubed theta plus sine theta cos squared theta, all divided by cos theta, is equivalent to tan theta. Now, there's a couple of things that you will need to learn in your studies into A-level maths that will make this question so much easier. Now, the 2 things you need to learn, one of which is that sine theta divided by cos theta is equal to tan theta. Now, you can do that from constructing a circle at the origin and incline a line at an angle theta to the horizontal and say, well, okay, definition of sine is the x value divided by the radius, or the y value divided by the radius, and tan theta is, and just use basic trigonometry. And you will see that that works. The other one is from Pythagoras' theorem, and quite often staff will call it the Pythagoras' theorem of trigonometry, and that is that sine squared theta plus cos squared theta equals 1. So we've got sine squared plus cos squared, and obviously the proof of those will come into the A-level mathematics course. It takes about 5 minutes to actually prove those, and it works for every single one. Now our question actually stated sine cubed theta, right? So the 3 there means that we're cubing the sine. So that if you've got 27 degrees, you'd work out sine 27, get your value of 0 point whatever it is, and then you'd cube it on the calculator. And then we've also got plus sine theta cos squared. And that's all over cos theta. And the examiner is claiming that that is equivalent to tan theta. So again, I'm going to do the left-hand side, right-hand side. I'm going to start with the left-hand side because it's a bit easier to work with there. More information, I can do more. So if we take the left-hand side, on the top line, I'm going to take out a common factor of sine theta. So the left-hand side, I'm going to write that as sine theta, and then in brackets, I've removed a sine theta from the sine cubed, so I'm left with sine squared. And then plus, I've removed the sine theta, so I'm left with cos squared theta. And I've done nothing to the denominator, so I'm just going to copy it down again. And there's nothing wrong in just copying something down, line after line after line, until I need it. So at the top of that, well, we've got that this bit comes from there. So that will give me sine theta divided by cos theta. And that's equivalent to tan theta. And that is the right-hand side. And there we have, we've proved it. As you can see, just a few short lines, but these two hints and clues, that sine theta over cos theta is tan theta, and sine squared plus cos squared equals 1. As I say, the majority of you will not have met that already. It is something new for the A-level, but you can see that it's not an onerous task to actually do those things. And the proof, as I say, can be done from a circle, center the origin, put any point on the circumference. Usually top right hand side is always the best one to start with. You have a horizontal distance x and a vertical height y, and then obviously the radius of the circle, call it r. Try to avoid using numbers if possible, because people get bogged down and they think only works if r is 7 or only works if r is 15 or whatever, rather than if the radius is r, it works for all of them, and we can become a little bit more generic. And that's effectively what we require from proof. We want that generic, it works for every single one. It doesn't just work for 5 or 10 or a million or 2 million or a billion. It works for every single value. Now, for those of you that are interested, there are worksheets and solutions for those of you that would like them. They will be put up as per usual for this particular set of videos. So you can contact us and we will provide you worksheets and solutions. They are in both English and Welsh. There is one little trick question that should be quite easy for everybody to do. But again, think carefully. Make it simple. The big option is keep it simple. If you want hard questions, I can give you hard questions, but let's make these